In this segment of the Module 7 lecture, we're going to look at an example where the sampling distribution of the mean is used. So in this example, we're told that the time that people ages 15 to 19 years of age in the US spend driving each day on average 25 minutes. A sample of 50 drivers ages 15 to 19 are randomly selected. Telling us to assume that the population standard deviation is 1.5 minutes. And they're asking us to first find the probability that the mean time the 50 drivers spend driving each day is less than 25.5 minutes. In part B, they ask us to find the sample mean of time driven by more than 90% of groups of 50 drivers. And in the last part, they ask us to find the interval symmetrically distributed about the population mean that will include 95% of the sample means based on samples of 50 drivers. All right, let's look at this problem. If you notice, we're not told what is the population distribution. We're not told if the population distribution is normal or not. So, but since the sample size is 50, then we can rely on the central limit theorem to safely assume that the sampling distribution of the mean is approximately normal. So we can proceed to use table 4 to find these probabilities. And table 4 is the table of standard normal probabilities. All right, so let's look at the first problem. So they ask us to find the probability that the average is less than 25.5. So as we did in chapter 6, the first step is to calculate the z-score. Now the z-score in this case, we take the average, which is 25.5, subtract the mean of the population that we know is 25, also divided by the standard deviation, which is 1.5, divided by the square root of the sample size, which is 50. If you perform this calculation, you will find that the z-score is 2.36. Then using this z-value, you go into table 4 and you will find that the probability that the random variable z is less than 2.36 is equal to 0.9909. And following what we've been doing all along is we explain this result. So we can say then that the probability that the daily average driving time of a random sample of 50 drivers ages 15 to 19 is less than 25.5 minutes is 0.991. All right, so this is the first problem, or the first part of the problem, I should say. Now, the sample mean of the time driven by more than 90% of samples of 50 drivers, that is, the probability that the random variable x bar is bigger than some average value, is the same as the probability of the random variable z being larger than some z-score value, and that probability is 0.9. So because this is larger than, and you remember that table 4 gives you probabilities to the left of the z-value. So to find the z-value that we're looking for and the corresponding x-value, we need to first use the complement of this probability. So the probability that z is less than some value c sub 0 is going to be 1 minus 0.9, which is 0.1. So we're using the complement. Now, with this probability, you go and look for it on table 4, and then you see that the closest probability to this is 0.1003. And this should be 0.1, not 0.01. And the z-value that corresponds to this probability of 0.1003 is minus 1.28. Now we use this formula, is the same procedure we did in chapter 6, and the only difference is now that to find the average, we use the population mean plus the z-value times the standard deviation but now divided by the square root of n, because we're dealing with the sampling distribution of the mean. So we replace the values that we know for the mean, the z value that we found, the standard deviation, divided by the square root of 50, and we find that x0 is 5.03. So again, the explanation of this result is that more than 90% of samples of 50 drivers will spend on average, or an average time on the road of 5.03 minutes. All right, so this is the result for part B. Part C, they ask us to find the symmetrical interval about the mean that includes 95% of the sample means of 50 drivers. So the probability we're looking for is the z random variable is between two z values, z1 and z2, and with a probability of 0.95. Now, since this interval is symmetric about the mean, then the remaining probability, so what is left outside of 0.95, we divide it equally between the upper and lower tail, as shown in this figure, so that the probability, in other words, to find z1, we use a probability that the random variable z is less than this z1, and that's for a probability of 0.025. To find z2, now we use a complement of this probability in the upper tail, which is 1 minus 0.025, which is 0.925. Now that we have these two probabilities, then you go on table 4 and you find z1 to be 1.96 for a probability of 0.025. And you can go on the table and find the probability of 0.975, and you will find that z2 is 1.96. But if you do not want to do that, then because you realize that this is a symmetric distribution, so the z2 value should be just equal to the z1, but instead of being negative, it will be positive. So you can use the symmetry of the distribution to find the upper value. Once you have the two z values, then we use these formulas to find the corresponding x value. And this is the same procedure that we learned in chapter 6, except that we're using now the standard error of the sampling distribution, which is this standard deviation of the population divided by the square root of n. So again, we know all the values. We determine the z values for the lower limit and for the upper limit. And we find that for the lower limit, the average is 24.584, and the upper limit is 25.416. So now that we have found these values, then we explain these results. So the interval symmetrically distributed about the mean that will include 95% of the means of driving time of samples of 50 drivers is from 24.584 minutes to 25.416 minutes. Again, this is an example of how you can use the sampling distribution of the mean to calculate probabilities. Now, these are somewhat far-fetched problems, so I'm not going to ask you to do any of this. I just simply wanted to illustrate through this example what you could do to calculate probabilities using the sampling distribution. We're going to use this approach later on when we find confidence intervals. All right, I will stop here, and then in the next section we will continue with the sampling distribution of the proportion.